Hi guys, my name is Mark. I'm studying engineering at Trinity College Dublin, and today we're going to tackle the higher level 2021 chemistry paper. Specifically, we're going to be looking at question 11, which is a multiple choice question, and it also covers the optional chapters at the end of the chemistry book that you might cover. So yeah, this section is worth 50 marks, just like every other question in the higher level chemistry. And yeah, let's get started. So here we have our question 11, and as it says here at the top of the page, we have to answer any two of the following parts, so A, B, C, and D. So there is, there's 4 parts here, answer any two, and they tend to come from different parts of the chemistry kind of curriculum. So if there's certain parts that you are stronger with, you can obviously pick them, but I highly recommend you give all of it a stab, purely from the standpoint that it's easier to, pick up marks, and you give yourself a little bit more breathing room if you do a little more, in case you make a silly mistake or accidentally do something like that. But yeah, so for each of those 2 parts, so 25 marks going for each of them, so a total of 50 marks going for question 11. Let's get straight into part A. In 11, part A, specifically part I, we are asked a question on ethene. So in this case, more ethene is produced industrially than any other manufactured organic chemical. And the question here we're being asked is name one or give one major use of ethene. Now there's several different ones that you might want to use here, but I have just a go-to one that I always go to. So my go-to answer for this type of question is that one major use of ethene is the making of ethanol. And in this case, it would be kind of making ethanol. And in this case, it'd be making of ethanol on an industrial level, just making massive amounts of it. And the reason I always use this one is because ethene here is very similar in just sounding from ethanol, so it's very easy to kind of keep them together. Other answers you could have are like making certain, things like polythene or plastics and stuff like that, which is also completely, correct. You can do whichever one you might have learned off in your book, but the reason I kind of just say making of ethanol is because it's just very easy to remember. Yeah, this question was worth a total of 4 marks, and the 4 marks are just kind of going for straight up answers. In this case, the answer in this case would be the making of ethanol, but very easy 4 marks to pick up. So yeah. In part 2 of this question, we were asked to draw a label diagram of the arrangement of an apparatus used to prepare and collect small quantities of ethene in the school laboratory, and to also examine its properties. So the important thing to know here is that we were being asked about ethene. And sometimes it can be really easy to just kind of keep going because maybe you've been doing a couple parts there on ethene, and then all of a sudden you might notice that they change it to ethine, and you can very easily lose marks like this. So first thing to know here is that we were being asked about ethene. Another thing to note here is that we were being asked about a label diagram. So this is kind of a key thing, is that we need to have our diagram obviously, but make sure it's labeled. And we're also not expected to kind of give like a paragraph explaining anything. So you just need to have a very well drawn out diagram with all of the pieces of information on it. So here is my diagram. Hopefully it looks familiar to you if you've done this yet. So I'm just going to basically go through it and label the different arrows and what they might be used for. So over here on the left we have this kind of this is our glass wool, and it is soaked in ethanol. So this is what this is kind of. Just this arrow here is kind of just gesturing kind of the glass wool being soaked in the ethanol. As well as this arrow pointing to the substance in the middle of the test tube. This is our alumina. So our alumina, and that is another way you could write that is aluminium oxide. That's also completely correct. Down here below we have our Bunsen burner, and you can really, instead of saying a Bunsen burner, you could just say kind of anything that provides heat. So just to be completely clear, a Bunsen burner. And over here we have a delivery tube, which is just going to deliver the gas produced in the test tube on the left into our beehive apparatus on the right, which allows us to kind of correctly work with the ethene gas. Over here on the right we have our ethene gas. So what we can see here, just kind of over here, is that it is actually bubbling up through the beehive shelf, and it is coming up through the water, and it is actually just accumulating in this kind of top bit here, which I'm marking in with a purple star. And that's kind of how we are able to collected in test tubes. But yeah, this diagram is sufficiently labeled. You don't actually need to have as many points as I do. As always though, if you have the opportunity to kind of give as much information as you can, I recommend giving you an extra few just in case you might get one wrong or forget something. This question was worth a total of 9 marks, and there was 3 marks going for each one of the 3 points that you picked. So in this case, I'm going to just pick these ones. So saying that the glass wool here at the end, that was 3 marks. Another one would be having this heat source over here, so this Bunsen burner. And another 3 marks, for example, could be, you know, our ethene gas being collected, or I could say even, yeah, we'll just say ethene gas being collected over here. So even if you just said kind of a general collection of ethene gas, or using even a gas syringe, if that's the way you learned it, that also works perfectly right. But this should be, that will bring you to your total of 9 marks. In part 3, we were asked to draw the structure of an organic product of the reaction of ethene in a solution of bromine. So, you know, this might come out of, you know, nowhere. You mightn't exactly know, you know, why they're asking me all of a sudden what happens if I react ethene and bromine. Just to kind of give you a reminder of where you might have seen this before, this is a saturation test for certain organic compounds. For example, you would mix ethene with you know, bromide water, or bromine water should I say, or in this case just a solution of bromine, and it's able to tell you if it's a saturated compound or an unsaturated compound. And in this question we're just kind of being asked to draw out that compound. So here I have drawn out kind of my kind of thought process about how to approach it. So on the left over here, this is our ethene. So our ethene here having a double bond between the 2 carbons and our 4 hydrogens around it. And as well as that, up here, I'm just going to draw it up here, we have our bromine solution. So in this case, I'm just going to say it's just bromine on its own being applied to it. And what happens is when you mix this bromine with the ethene, it actually breaks down that double bond in between the carbons, and it creates something looking like the molecule we have on the right, which I have labeled down here as 1,2-dibromoethane. Reason it's, you know, the 1,2 is going to represent the fact that these bromine groups are actually on the first and second carbons. So that's where we're getting the 1,2 from. And the di here meaning that there's 2 bromines present, so diabrom means there's 2 bromines. And the ethane is just kind of, and the ethane is signifying just the general shape of the molecule. Ethane has 2 carbons, and it will have you know, 3 hydrogens around each of those carbons. So if we're replacing the two of those hydrogens with bromines, that's when we get 1,2-dibromoethane. So that's the final molecule that we were looking for. You didn't need to name it, but personally, if I was just kind of drawing it out like this, just to kind of explain where I'm getting it from, I would. So yeah, this is the final answer. The marks going for this question was a total of 6, and yet again, it was very, very simple breakdown. You just got 6 marks for correctly drawing out the molecule over here. One thing to note is these bromine groups, just I'll circle them here in yellow, and these 2 bromine groups can be placed with kind of different places around the molecule. As long as 2 bromines are not centered off the same carbon, it's fine. So you could put a bromine, you know, you could put this bromine over here on the right, you could put this over here if you wanted to, or you could put it over here. Doesn't really matter, just as long as there's 1 bromine connected to 1 carbon and the other bromine is also connected to the other carbon. In part 4, we are asked, or should I say we are told that the diagram above shows an arrangement of an apparatus used to compare the solubilities of ethene in water and also cyclohexane. We were asked to explain, based kind of, you know, on that, how and why the solubility of ethene is different from that, you know, solubility, should I say, of, and we were then asked to explain how and why the solubility of ethene in water differs from its solubility in cyclohexane. So basically we're being asked, why does ethene dissolve differently in water and cyclohexane? The answer to this kind of relies on a good bit of knowledge that hopefully you'll come across during your course, mainly centering around bonding, covalent bonds, and, you know, the types of molecules that you can have, so non-polar and polar. And here I have my answers, so just going to go through it first and then hopefully I'll go back and explain. So here I've said ethene is soluble in cyclohexane and insoluble in water. This is because ethene is a non-polar molecule and cyclohexane is also non-polar, while water is a polar molecule. Ethene has a similar intermolecular forces to cyclohexane, and this allows ethene to be soluble in cyclohexane yet insoluble in water. So basically, ethene itself is soluble in cyclohexane and insoluble in water. So this part here would be kind of the answers that they're looking for. But another important thing to note, because it's asking how, another thing to note though is we're being asked why. So this second half of the kind of question is going to hopefully answer that why. The reason that ethene is soluble in cyclohexane is because ethene itself is a non-polar molecule and cyclohexane is also a non-polar molecule. An important thing to note here is that ethene has similar intermolecular forces to cyclohexane, and that makes it easier for ethene to dissolve and be soluble in general in cyclohexane. While if we take a look at a water molecule is a polar molecule and has quite different intermolecular forces to that of ethene, and as a result it can be a little bit more difficult for it to be soluble in water. So basically the key things to take away here is ethene has similar intermolecular forces to cyclohexane, thereby making it soluble in the cyclohexane, and as a result, because water has different intermolecular forces to ethene, it makes it difficult for it to be soluble in the polar water. The marks for this question were broken down as follows. There was a total of 6 marks going, and you got 3 marks for saying how and 3 marks for saying why the solubility of ethene in water differs from that in cyclohexane. You got 3 marks for saying ethene is soluble in cyclohexane, so this top line up here, and also that it's insoluble in water. And then for this second half of kind of the explanation, you also got 3 marks. So in this instance, you got 3 marks for saying that cyclohexane is nonpolar and water is polar, and that as a result of the fact that ethene has similar kind of intermolecular forces to cyclohexane, that is why it would be soluble in that, but also insoluble in the polar water. Moving on now from part A and onto part B, we are asked a question on water and biochemical oxygen demand. At the start of part B, we were given a paragraph kind of giving us a bit of information about biochemical oxygen demand. So in this case, we're told that pig slurry has a very high BOD, and therefore effluent from pig farming must be very carefully managed. And in part I, we were asked to explain the underlying terms. So in this case, we're being asked to explain biochemical oxygen demand. Unfortunately, this is just kind of a straightforward definition, but I'm going to try and give you a little bit of clarity to what's behind it. And here we have our definition and explanation for biochemical oxygen demand. So from here on, I've kind of just referred to it as BOD just because it's shorthand. But in this case, BOD refers to the amount of dissolved oxygen consumed by a biochemical process in a sample of water over a 5-day period whilst water is being stored in the dark at 20 degrees. So there are a few kind of important buzzwords to note in this definition and explanation. The key ones being here that BOD refers to this, the amount of dissolved oxygen. So it's this amount or measure of the dissolved oxygen in the sample that is being kind of consumed or dissolved, should I say, by biochemical processes. So these could be biological, by small bacteria, or otherwise. And just to give it a bit of time frame to the definition, it's said that this is said to be in a sample over a 5-day period, whilst it's being stored in the dark at 20 degrees. So the reason that they have a time period and kind of describe the conditions in your kind of definition here is so that when you're trying to measure the BOD from different samples, you don't want to be measuring them over different amounts of time, because if you have bacteria in a sample, if you leave them for a couple of days, they're going to dissolve a certain amount of oxygen, or should I say consume a certain amount of oxygen. But if you leave them in there longer, they're going to be in there, they need more oxygen, so that they'll take out more or consume more, which results obviously in a different answer. So making sure that you have kind of that 5-day period also, as well as being in the dark at 20 degrees, just kind of standardizes the definition. The breakdown for the marks goes as follows. There was 6 marks going in total, and there was 3 marks going for saying that it is referring to the amount of dissolved oxygen consumed by biochemical processes. So saying that, biological, bacteria or anything kind of like that is dissolving oxygen. That's the first 3 marks. And then you got another 3 marks for talking about the standardized amount of time and conditions. So in this case, 5-day period while it's being stored in the dark at 20 degrees. That's where you got your other 3 marks from. In part 2 here you're asked, why is the runoff from pig slurry fertilizer or the addition of any other solution with a high BOD into waterways undesirable? Yet again, this is just kind of a theory question and is a fairly straightforward theory answer, but as always, I'm going to hope to give you a little bit more insight as to the reasoning behind it. In this case, the reason that you don't want to add high BOD solutions into waterways is because it is undesirable due to the fact that it can cause algal bloom. In this definition here, the term algal bloom is your buzzword, so that's kind of where the marks are going for. But the reasoning behind this is because when you add kind of solutions with high BOD into a waterway, what can happen is the bacteria being added into this water in those samples, for example, in this pig slurry, what can happen is it can consume a lot of the oxygen dissolved in the water, and this can result in different forms of pollution or deoxygenation of the water, killing fish, making the water unable to drink, and as a result of this, it can also lead to algal bloom. So any of those answers are also completely correct. In this case, I just went with algal bloom because it's an easy one for me to remember personally. But that is why it is undesirable to have high BOD solutions in waterways. The total marks going for this section were 3 marks, and yet again, fairly simple. The 3 marks are just going for that buzzword, so algal bloom, but you could also have said anything along the lines of deoxygenation, or killing fish as a result of it, making the water unfit for drinking. Whichever one you find easiest to remember, these are all completely fair answers. In part 3, we were asked, how could a process like the secondary stage of sewage treatment reduce the quantities of organic matter in pig slurry? So the important thing is we're being asked, how can it reduce, or should I say, the quantities of this organic matter in the pig slurry effluent? And here we have our answer. The secondary stage of sewage treatment works by the oxidation of organic matter via a biological process. So those are buzzwords here underlined. And basically the second stage, or should I say the secondary stage of sewage treatment is kind of based around the fact that organic matter will break down and digest this organic matter in the slurry. So by adding these kind of organic, just kind of these bacteria, as a result of adding kind of just microorganisms or bacteria in general, which I'm kind of just lumping together in the term biological process, making sure that you include the fact that microorganisms or bacteria, you could say either of those are also completely valid answers. But by saying any of these biological processes, what they do is they'll break down, oxidize, and actually digest this organic matter, and that is the way that we remove such large quantities of organic matter in this pig slurry, because these bacteria will come in and they will break it down and they will digest it for themselves, and it actually is one of the important stages that we have of sewage treatment. The breakdown of marks for this question go as follows. There was 6 marks going in total, and you got 3 marks for saying that it is the oxidation or the breaking down of this organic matter, and you got another 3 marks for saying that it involves microorganisms or bacteria, or I've in this case just said biological processes. So if you said by microorganisms, that's also completely fine, or if you said by bacteria, that also completely works. In part 4 here, we are given kind of quite a large paragraph here, telling us some information about a sample of pig slurry which was diluted, and then after it was diluted, it was tested for BOD, or should I say it was BOD tested, and we were told that the difference in the dissolved oxygen concentrations between the first test and the second test was 2.7 ppm, which also stands for parts per million. And in part 4, we were actually asked, why was the raw slurry diluted and aerated before analysis? The sample was diluted and aerated, otherwise all the oxygen would be consumed between the analyses whilst it was kept in storage between the 2 tests. So the important thing to note here is that in the question, or should I say like in this paragraph that we're being given, what happened was this slurry sample was taken, it was diluted to 5 litres, and then another sample was also taken. The first sample was immediately tested after being harvested, so we got kind of an instant almost BOD results. We knew exactly the amount of dissolved oxygen present in that sample, but the second sample was given a few days between being collected and analysed. So as a result, the bacteria dissolved inside of the sample itself would have consumed some of the oxygen present, and this would result in a different BOD. By aerating and diluting the slurry, this kind of reduces the likelihood of this happening, but it also ensures that there is oxygen present in the sample that's been kept in storage over those 5 days, because if not, it would all be gone but by the time they tested it. The total marks going for this question was a total of 6, and those 6 marks are just kind of going for saying anything along the lines of the fact that the oxygen would be consumed between the two kind of analyses, or saying that the BOD present in the sample would be greater than the oxygen available, and as a result it would use all of it up. Anything along those lines would be 100% right in this case. In part 5, we were asked to calculate the BOD of the raw pig slurry. So in order to do this, we need to use the information given to us earlier on in the question. So I'm going to go back to that and we can start there. Going back to the question here, I'm just going to highlight the paragraph that we were looking at earlier. So here on the right, we have the paragraph that we were reading through about the raw pig slurry sample. And what we know is that a 50 centimeter cubed sample was taken, it was diluted to this 5 litres, and then it was well aerated. And then finally, another 50 centimeters cubed of the same diluted solution was then diluted further in the same way to 5 litres. So basically what we did is we started out with a 50 centimeter cubed raw pig slurry sample, and then we diluted it to 5 litres, and then took a subsection of that and then diluted that again to another 5 litres. So this is a very dilute solution. Another key thing to note here is that we have a difference of oxygen concentrations between the two analyses being 2.7 parts. Using all this information, we can actually work now to find the BOD of the raw pig slurry. A dilution factor is basically how much a solution is diluted by. If I start out with a 10 centimeter cubed solution of, for example, ethanol, and then try to dilute it to a litre, the way I come to that is by dividing our final volume by our initial volume. In that case, it would be 1,000 divided by 10, because there is 1,000 centimeters cubed in a litre. Similarly to that, we need to find our dilution factor in this case. What we know is we started out with a 50 centimeter cubed portion, and this was then changed to a 5 litre portion. Important thing to note here is that 5 litres is the same as 5,000 centimeters cubed. Therefore, in this stage, we have a dilution factor here of 50, or should I say 5,000 divided by 50, which is exactly the same as 100. The reason this is only for stage 1 is because, as we noted earlier on in the question, a sample was diluted to 5 litres, and then a subsequent subsample was taken and then diluted again to 5 litres, basically meaning that what we did is we diluted something twice. Now going on to the second dilution factor, because as we said earlier, we diluted twice, another 50 centimeters cubed sample was taken and it was diluted to 5,000 milliliters, or should I say 5,000 centimeters cubed, which basically means another dilution factor of 100. So just to write this out, 100 being our second dilution factor. What this basically means is that in order to find the original solution and how much it was diluted to get to this final solution, we have to multiply it by 100 times 100, so basically 100 squared. And now is where our 2.7 parts per million comes into play. The dissolved oxygen concentrations between the two analyses was 2.7 parts per million. What this means is that the sample, 2.7 parts per million were lost, and that means if we multiply that by our two dilution factors, we'll be able to find the amount of dissolved oxygen consumed in the raw pig slurry. Writing this out fully, what we're going to have is our 2.7, and we're just going to multiply that by 1,000, or should I say 100, which is our first dilution factor, and then multiply it by 100 again, which is our second dilution factor. Once again, the reason we're multiplying by 100 twice is because we diluted it once and then took another sample of that and then diluted it again, which basically means that we diluted it twice. Plugging this into our calculator, we're going to have 2.7 times 100, and then we're going to multiply that by 100 again, and we're going to get a value of 27,000 parts per million. So basically 27,000 parts per million is our BOD for our original pig slurry sample. So I'm just going to write that out now in full. So it's going to be 27,000 parts per million, so ppm stands for parts per million, and yeah, that's our final answer. So in this case, there was 4 marks going for this question, and the breakdown was fairly simple. There was just 4 marks going for your final answer, but I hope was able to give you a little bit of insight as to kind of why you have to multiply by 100 and why you have to multiply by 100 twice in this instance, because you are diluting the sample twice. Now we're going to move on to part C. So in this case, part C is a question on kind of the fundamentals of chemistry, looking back into the history of chemistry, and just a kind of a few questions about atoms and atomic theory in general. As always, with these types of questions, there tends to be a paragraph given to you with a bit of information. So if you read through this paragraph, you'll see that it's talking about John Dalton and his kind of discoveries and his role he played in kind of just chemistry and how it has progressed throughout the years. In part I, though, we are asked about a photograph, and yeah, let's get straight into it. In part I, we are asked about a photograph which contains several kind of wooden balls here used by John Dalton to represent atoms, and we are asked what is Dalton's atomic theory. So this is just kind of a straightforward definition, and you know, hopefully if you've kind of looked over the start of chemistry, I know I kind of forgot about it when I was studying for the Leaving Cert, but they tend to ask a lot of questions and the marks are very easy to pick up. So in this case, Dalton's atomic theory is just a very small kind of like one word answer, or should I say one sentence answer, and a very easy place to pick up marks. Dalton's atomic theory was that matter is composed of tiny particles called atoms here being kind of like the buzzword, which are all indivisible. So this kind of just in one sentence gives you all the information you really need to know. John Dalton believed that matter was composed of these tiny particles. He called these tiny particles atoms. And finally, he believed that they were basically indivisible, or another way you could say that is they cannot be split up or broken down any further. The marks going for this question was a total of 6, and you got 3 marks for saying kind of the important thing was saying that he believed that matter is composed of these tiny particles called atoms, and you got another 3 marks for saying that they were indivisible. There were another few pieces of information that you could have said here. You could say atoms cannot be destroyed or created, or that there is a fixed number of atoms in our universe, or another one that you could have said is that atoms of the same element are completely identical. But in this case, these are the first 2 points that always come to my mind when I think of his theory, purely from the fact that they're very closely related. But yeah, very easy place to pick up 6 marks. In part 2, we are asked to name the scientist whose work on cathode rays led him to identify the electron as a subatomic particle. So the kind of the giveaway here is his work on cathode rays, and this is just kind of a one word answer, and it's just someone's name. Important thing to know here is that you don't really get any marks for saying their first name. Their second name is the key thing to get right. The answer that we were looking for here is J.J. Thomson, and yeah, this is kind of just, it's just kind of, you know, you either get it or you don't. And there was 3 marks going for this, and you just kind of got the 3 marks if you got it right. The JJ here, though, wasn't, you know, necessary, but Thomson is the word that they're looking for. In part 3 here, we are asked what happens in a radioactive nucleus when beta decay occurs. So beta decay here is one of the 3 fundamental types of radiation, or should I say radioactive decay, that you'll study at Leaving Cert Chemistry. You have alpha decay, beta decay, and gamma decay. It's important to know the differences and kind of what occurs when something goes through alpha or beta decay or gamma decay even. But yeah, in this case, we're being asked about beta decay, so try not to get them mixed up if possible. The answer to this question goes as follows. In beta decay, a neutron inside the nucleus of the atom decays into a proton whilst emitting an electron. So these are kind of the buzzwords here that I've underlined. And basically what happens inside of this nucleus of the atom is that one of these neutrons present will decay, and when it decays, it'll split into a proton and an electron. The proton will remain inside of this nucleus, and the electron will be kind of fired out from the nucleus. So this was a question worth a total of 6 marks, and the breakdown was as follows. You got 3 marks for saying that it decays into a proton, and another 3 marks for saying that the electron is emitted. So a very simple and very easy place to pick up those 6 marks. This type of section, especially on you know, the history of chemistry, is a great place to pick up marks, and this is a perfect example. I always loved radioactivity. I thought it was a very nice chapter, something I was able to pick up quite easily. And if you see the same, you know, if your opinion on it was the same and you kind of understand it quite well, this is a great place to pick up marks. In part 4 here, we're given a big block of text, as always with these types of questions, and we are told about the measurement of relative abundances of an isotope, and we were told about some guy who was doing it, the results he got, and it seems he was working with neon quite a bit. And what we were told here is that neon atoms have a mass number of 20, and the remainder had a mass number of 22. So basically a portion of his results and work on neon found that the mass number was 20, but some said that the mass number was 22. What we're asked here in part 4 is what is now the accepted composition of a neon 20 atom and a neon 22 atom in terms of these subatomic particles. So when it says subatomic particles, it's talking neutrons, protons, and electrons. And here we have our answer. Now, I'm going to go through the way to approach this type of question after I've gone through the answer, but in this case, neon 20 is represented as 10 protons, 10 neutrons, and 10 electrons, and neon 22 is represented as 10 protons, 12 neutrons, and 10 electrons. Now, the way you want to approach this is the first thing you want to do is look up neon in your periodic table. What you'll find is that it is 10th in the periodic table, or it's going to have a 10 as its atomic number. Another thing to note here is that as a result of 10 being its atomic number, that's where we get these 10 protons from and our 10 electrons. If I looked up the periodic table and I found another atom with an atomic number of 7, that means that there'll be 7 protons present and 7 electrons. Similarly for neon 22, because neon is still number 10 on the periodic table, it's also going to have these 10 protons and 10 electrons. That's not going to change. What does change though here is this thing in the middle, our number of neutrons. In this instance, our neutrons is kind of the difference between the mass of the particle, or the mass of the atom, and the number of protons. So if you look up in the periodic table, what you'll find is that the mass number will be in and around 20. For example, in this case, neon 20, which is what we're being asked about, the mass is 20, and that means that we're going to have 10 protons, and then you take 10 away from 20 and you'll be left with 10, which is our remainder, or our number of neutrons. So in this case, that's where we get 10 here as our number of neutrons. Applying the same kind of idea to neon 22, neon 22 has a mass of 22, and what that means is if I take away 10 protons from 22 is our total, we'll be left with the number of neutrons, which means that we get our total of 12. And both of these are what we call isotopes, which have the same number of protons but a differing number of neutrons. The marks going for this question, there were 6 marks going for this question, and the breakdown was as follows. You got 3 marks for correctly breaking down the subatomic particles in neon 20, and you got another 3 marks for correctly breaking down the subatomic particles present in neon 22. In part 5 here, we are asked to calculate the relative atomic mass of neon using Aston's results from above. Basically what this means is that we need to use the information given to us in the paragraph that we were given above, and use this to find our relative atomic mass. Now, just to paraphrase the big paragraph that we had above, what we know is that he found that 90% were equal to neon 20, and the remainder, so that would be 10%, were equal to neon 22. So basically what that means is that when he went out and he measured all the neon, he was able to find that 90% of it was the isotope neon 20, and 10%, or the remainder in this instance, was neon 22. What we need to do now is kind of find the relative atomic mass of it, which is taking into account all the relative abundances found in nature. So this neon 20 and neon 22 need to be weighted kind of in how much is present in the results that Aston found. The way we're going to do that is by multiplying 90%, or in this case 0.9 times 20, and then we're going to also add this to 0.1 or 10% times 22. And what this basically means is if 90% of the atoms are 20, and then we add to that the 10% which are 22, it'll give us a relative abundance of neon present, so it'll give us the relative atomic mass of neon. By plugging this into our calculator, we should get our answers. So what we're going to do is have our brackets here, and it's going to be 0.9, or you could just say 90%, making sure to obviously convert them to decimal. So 0.9 times 20, and then we're going to have to add on to that our 0.1 times our 22, and then this should give us our answer, which in this case is 20.2. This means that the relative atomic mass of neon, according to Aston's results as shown above, is 20.2. There were a total of 4 marks up for grabs in this section, and it was fairly simple to break down in this instance. And there was kind of 2 marks going for writing out this kind of the formula in general, and final 2 marks for getting your answer. Another way you could have approached this is by saying 90 times 20 and plus 10 times 22 would give you 2020, and then divide that by your total mass. So let's just say divide that by 100, change from your percent to your decimal, and that would give you the same answer. But this is just kind of the way I always did it. It just means that you have to skip out that dividing by 100, and just means there's one less thing to forget while you're doing the question. In part D, we are asked to answer part A or part B. This is the section that kind of is more associated with the additional different types of chapters that you'd find at the end of your chemistry book, stuff like atmospheric chemistry and the manufacturing of periclase and things like that. In this case, for this video, we're going to be having a look at part A and part B just to give you the kind of full idea and run through of the question. Let's start with part A. Part A in this case is asking us a question about the nitrogen cycle. That means that this question is based on atmospheric chemistry and that whole chapter of optional chemistry. So you may or may not have covered it, and if you haven't, then unfortunately you can't attempt this question, and that's just how it goes sometimes, but you may be able to do part B, and if not, you have 3 other parts you can attempt for the rest of question 11. In part I, we are asked, why is nitrogen gas unreactive? This question is kind of going to be asking us a little bit more about intermolecular bonds and actually what nitrogen gas is and how it's found in nature. The answer to this question goes as follows. Nitrogen gas is composed of a triple bond between 2 nitrogen atoms, which is very difficult to break. This is due to the high degree of symmetry found in the molecule, and also as a result of this makes the gas itself very unreactive. Now, to go through this in a little bit more detail, nitrogen isn't normally found out in nature on its own. It's normally found in the form N2. This is because nitrogen just tends to bond with itself as a diatomic element. This means that it can be written as N2 or also N with a triple bond between them. When 2 nitrogen atoms bond together, they do so by using a triple bond. This triple bond is extremely strong and difficult to break and requires a lot of energy to do so. In order for nitrogen gas to be reactive, it means that this gas, or should I say this diatomic element, should be very easily broken apart so it can react with other elements as it finds fit in nature. Because nitrogen has a triple bond, it means it takes a massive amount of energy for this to occur, and as well as this nitrogen molecule, N2, has a very high degree of symmetry. This also kind of adds into making it an extremely unreactive gas in general. The total marks going for this question was 4 marks, and the breakdown goes as follows. You got 2 marks for mentioning that there was a triple bond present between the 2 nitrogen atoms, and you got the other 2 marks for saying that there was a high degree of symmetry, or that the molecule was nonpolar, or kind of anything like that. Just another piece of information kind of adding to the reason why nitrogen gas itself is unreactive. In part 2, we were asked to describe, using equations or otherwise, how lightning generates the gases NO and NO2. First, I'm going to describe them and how they're formed using kind of just words and a little bit of description, and then I'm going to also give you the equations as well, just to hopefully give you a little bit more insight as to what is happening. First and foremost, let's have a look at the gas NO. NO, or nitrogen oxide in this instance, I'm just going to call it, is formed when nitrogen and oxygen combine in the atmosphere to form NO. Now, if we're to look at this purely from an equation standpoint, the way we'd write this is as follows. N2 plus O2, so nitrogen plus oxygen, is going to change into 2NO. In this case, NO here is kind of the gas that we're looking to describe or show how it's formed, and N2 is our nitrogen and O2 is our oxygen. So when they combine in our atmosphere, they go on to form NO. As for NO2, NO2 forms when NO mixes with oxygen to form NO2, basically using a product of the previous reaction to create the new NO2 that we're looking for. To write this in terms of an equation, I'm going to do so now. NO, found in the atmosphere, is going to mix with oxygen to go on to form NO2. This is kind of as we expected following our word description. Now, as always with this question, we are asked you can either do it in words or in equations, so either one is completely perfect and you're going to get full marks. I just felt it'd be best to give you a little bit more insight as to what's actually happening. In this case, there was 6 marks going for this question, and the breakdown was fairly simple. You got 3 marks for correctly answering how NO was formed, and you got another 3 marks for correctly answering how NO2 was formed. Doesn't really matter, which way you did it, whether it was with equations or with words. In this case, I just wanted to give you guys a little bit more insight into what's happening. In part 3, we are told that atmospheric NO2 lowers the pH of rainwater. We are then asked to write a balanced equation for the reaction of NO2 with water forming acid rain. Unfortunately, this itself is just another formula that you probably going to have to know of, but you can try and do your best without knowing it by just simply reading the question and remembering kind of the components that are required. To write this out, what we know is we're going to be mixing H2O, which is our water, in our atmosphere with NO2. From the question, we know that H2O, or water, is going to mix with NO2 to form some form of acid rain. The question now becomes, how do we write this? In order to balance this correctly, we're going to need to put a 2 in front of our NO2, and then this is going to convert into HNO2 plus HNO3. In this instance, here we have proven, or should I say, here we have shown that when water mixes with NO2 in the atmosphere and the equation is correctly balanced, what we get here on the right hand side is HNO2 and HNO3, which are components of acid rain. There were 6 marks going for this question, 3 marks for correctly balancing the equation, and another 3 marks for correctly kind of just writing out the formula. So the first 3 marks here is going to go for our formula, and these other 3 marks here are going to go for balancing the equation correctly. In part 4, we are told that rainwater, or should I say this rainwater, forms nitrate compounds in the soil that are absorbed by some plants through their root systems. What use do plants make of these nitrate compounds? The question kind of boils down to what do plants use nitrate compounds for, and you might touch on this in biology, I'm not 100% sure, but in this case it is kind of a key part of the nitrogen cycle and how nitrogen itself gets used by kind of just plants and plant life in general. The answer to this question here is that plants use these nitrates in the making of protein, or in this case amino acids, which are completely, they're synonymous. You'll get full marks if you use either one of them. And thankfully, because this is just kind of like a one-liner answer, there was 3 marks going for the question, and you got those 3 marks by simply mentioning either protein or amino acids. Both are completely correct. In part 5, we were asked to describe one pathway by which nitrogen in animals is restored to the atmosphere, completing the nitrogen cycle. So we're basically asked to how do we finish off the nitrogen cycle going from the animal stage back into the atmosphere. Now, depending on how well you know the nitrogen cycle, I believe you also cover this in biology, so there is a good bit of overlap here and you might get lucky if you do both. But in this case, I'm just going to write out kind of the definition and kind of give a little bit more context as to what is actually going on. So the answer goes as follows. When an animal dies and decomposes, the ammonium compounds that are created are then converted to nitrogen compounds by bacteria, which are ultimately changed into nitrogen. Now, although this line kind of might make 100% sense to you, I'm going to give you a little bit more context to what is happening. Following an animal's death, it actually begins to decay and decompose, and the animal becomes kind of an animal waste. And ammonium compounds are then created by the bacteria in the body, which are then, excreted or egested. Bacteria then go on to convert nitrogen compounds, such as nitrates, nitrites, kind of ammonia as well, to nitrogen N2, which are then, found in our atmosphere, thus completing our nitrogen cycle. Key things to note in this answer. One is that when animals die and decompose, so a key word there is decomposing or decomposition, so when the animal begins to break down. Another key term here is ammonium compounds, and when these ammonium compounds are then created, bacteria go on to convert the nitrogen compounds into nitrogen, which we actually find in our atmosphere as it is. Because this question has a few parts to it, there is, you need to get 2 of them correct in order to get your full marks. So there's 6 marks going, and you got 3 marks for correctly, talking about the ammonium compounds and the death and decay of the animal itself. So that's where you got your first 3 marks from, and you got your final 3 marks for, commenting on that bacteria and break down these nitrogen compounds and go on to form the nitrogen which we find in our atmospheres. And you get your final 3 marks for saying that the bacteria and then go on to convert these nitrogen compounds, such as nitrates, into nitrogen, which we then find in our atmosphere. Now that we've had a look at part A, we are going to move on to part B. In this case, part B is going to be asking us about electropositive metals, a little bit more on electrolysis, as well as our electrochemical series. So these kind of tend to come together as one of our final chapters, and if you've covered it, I highly recommend you take a stab at it, because there's no harm if you've got extra time to give yourself the best chance of getting more marks in your exam. In part I here, we were given a big block of text, as always with these types of questions, and we're told some information about electropositive materials, or should I say metals, and how they are extracted from their ores by a process known as electrolysis. In part I, we were asked to explain the underlying term. In this instance, the underlying term up here is actually electrolysis, so we need to kind of give a bit of give a bit more context, a little bit more information about electrolysis. The following explanation will hopefully give a little bit more information on what electrolysis is. Electrolysis is the breaking down of a chemical or a substance by the passage or usage as well of electricity. So there's a few key like buzz terms that you want to include in your answer here. One of them obviously is by the passage of electricity or the usage of electricity, and the other one is the breaking down of a chemical or a substance. So in this case, what happens is when you pass a strong electric current through something, what will happen is the molecules can break up or they can form new ones, and what eventually happens is the chemical substance itself is broken down, and in this case we know that it is used to extract metals from ores. In the example given above, we're told that aluminium and sodium can be extracted from their ores by use of electrolysis. In this question, there was a total of 4 marks going, and the breakdown went as follows. You got 2 marks for correctly saying how that the passage of electricity will break down, a chemical or a substance, and you got another 2 marks for, mentioning that it was due to this passage or usage of electricity. That's very important because electrolysis, it's kind of in the name. Just to, if in case you forgot, it is kind of mentioned in the name, so it's not too bad. It is just the passing of electricity to break up a substance. In part 2 here, we are told aluminium is extracted from molten aluminium oxide by electrolysis. We are then asked, why must the aluminium oxide be molten? The answer to this question goes as follows. In order to extract the aluminium, the oxide must be molten in order to allow the ions to be free and to allow them also to move around. This allows the aluminium in the compound to be extracted. So basically, by heating up and actually creating, or should I say making the aluminium oxide molten, what happens is the ions present are free to move around. They're not exactly bound anymore and not held so rigidly. As a result of this, it means that the aluminium itself is significantly easier to extract from the compound, or in this case the ore. So it just makes it so much simpler to take out the aluminium from the aluminium oxide. A few key things to note in this definition, and the main and really important thing to write down here is that this is all done so that the ions are free to move around, and that's why it actually is easier for the aluminium oxide, or should I say the aluminium, to be extracted, is when it is molten, the ions are free to move around. So that's the key term that you want to include. This question is worth a total of 3 marks, and you kind of just got 3 marks for mentioning that the ions are free to move around. It was kind of like the key term that you needed to include in order to get all your marks. In part 3, we were asked to write the balanced equations for the reactions that occur at the graphite electrodes and for the overall reaction during the electrolysis of aluminium oxide. This means that we're going to have 2 reactions here for the graphite electrodes, 1 at each electrode, so we're going to have 2 half reactions, and we're also going to have an overall reaction happening, so we're going to have a total of 3 kind of chemical formulas, or we're going to have 3 equations written down. An important thing to know here is that this question has a lot of similarities to redox and oxidation and reduction that we've done earlier on in the chemistry course. A quick way to remember, anytime I think of redox, the first thing that comes to my head is the acronym oil rig. Oil rig is just a quick way to remember kind of the relationship between oxidation and electrons and reduction and electrons. I'm now going to write down oil rig and kind of explain where it comes from, and we're going to use that to solve this question. Now, writing down oil rig, I'm going to go through each part of the acronym. O is going to stand for oxidation, I is going to stand for is, and L is going to stand for loss. O is going to stand for reduction, I is going to stand for is, G is going to stand for gain. What this basically means is that oxidation is loss, or the loss of electrons, and reduction is going to be the gain of electrons. Using oil rig, we can now correctly approach the graphite electrodes from an anode and a cathode perspective and correctly write down the chemical formulas that we need for the reduction and oxidation of the aluminium oxide at each electrode. At one of the electrodes, what's going to happen is electrons are going to be pumped in. This means that there's going to be a gain of electrons. At one of the electrodes, electrons are going to be pumped in to the substance. They're going to be pumped into this aluminium oxide. This is going to result in the reduction of the metal. This can be represented by the formula Al3 plus 3E minus is going to go into Al. What is happening here is on the left hand side, electrons, or in this case 3 electrons, are being pumped into our aluminium oxide. Al3 plus in this case is representing the aluminium in the aluminium oxide. It has a 3 plus charge because the oxide will counter it out or make the whole thing neutral. So in this case, the aluminium on its own is going to have a positive, or should I say in this case it'll be a 3 plus charge. And once we add those electrons coming in from the electrolysis, what's going to happen is the aluminium 3 plus is going to change into just aluminium. Approaching the other electrode now, as we said earlier, reduction is going to be the gain, so we've already covered the reduction part of the electrodes, and now we're going to look at oxidation. Oxidation is the loss, which means that electrons are going to be taken out. Instead of having plus electrons on the left, it means that we're going to actually have plus electrons on the right hand side because they're being taken out of the material. If aluminium oxide has the formula Al2O3, this means that our oxygens are going to have a charge of -2. Since we are taking electrons out, this is going to result in the formation of a half NO2 plus 2 electrons. Basically, what's happening is electrons are being taken out of this O2 minus ion and are going to result in the creation of half an O2 molecule and these 2 electrons which have been taken out. These are the 2 chemical formulas which are going to represent what's happening at the graphite electrodes. Now we have to approach the formula for the overall reaction. Bringing these 2 together, we can actually use this to build the overall reaction. To start with, what's going to happen is Al2O3, which is our aluminium oxide, is going to break down. The overall reaction is going to look as follows. Our Al2O3, or our overall aluminium oxide formula, is going to break down as follows. We're going to get 2 aluminiums plus 1.5 O2s. The reason that this occurs is if we look at the formulas above, we have Al3 plus and O2 minus. In order to balance these charges, we're going to have Al2 and O3. That means on the left hand side we're going to have 2 aluminiums, and on the right hand side we're going to have 3 oxygens. By using this, it means that by bringing the 2 formulas together, on the right hand side we're going to be left with 2 aluminiums, and as well as this on the right hand side we're going to be left with 3 half O2s. So we can represent this by saying 1.5 O2 molecules. This is one of the trickier questions, and I remember struggling a lot myself with this type of question, especially the redox reactions. I was never very good at it, but in this case, oil rig is a really powerful and useful tool, and it helps you remember kind of what's happening at each of the anode and the cathode. And in this question there were 3 equations required, which means that there was a total of 9 marks, each equation being given 3 marks. So if you got each one right, so this one on one of the graphite electrodes, the second one here at the other graphite electrode, and then finally our overall one giving us the final 3 marks, leading to the total of 9 marks. In part 4 we are asked to identify the chemical method used to extract iron from iron ore. The following is the answer to this question. Reduction in a blast furnace is used to extract iron from iron ore. The key term here being reduction. As we said above, when we were analysing the formulas that were associated with the reduction and the oxidation of the aluminium oxide and how electrolysis actually separated it into just aluminium and oxygen, in the same way iron can be extracted from iron ore. In this case, in order to extract the iron from the iron ore, instead of needing both oxidation and reduction, we just need the reduction of the iron in a blast furnace, and this helps liberate the iron from the iron ore itself. The buzzword in this question was reduction, and it was kind of the key one here. Making sure to mention that happened in a blast furnace was less important, but just as long as you mentioned the word reduction, you would get your full marks. Because this was a nice and short and simple question, there was only 3 marks going, and those 3 marks were given to getting the buzzword reduction in this question. In part 5, we were asked to suggest a reason why strongly electropositive materials were not isolated before 1800. It's important to understand exactly what an electropositive material is before you attempt this question. The first thing to note here is what an electropositive metal is. An electropositive metal is one that has a tendency to donate electrons and form well-charged cations. As a result of this, the metals themselves become positively charged. Now that we better understand the answer to what an electropositive material is, or electropositive metal, we can now attempt the question. In this case, an electropositive metal was not found, or should I say isolated, before 1800 because electropositive metals were not isolated before 1800. Now that we have tackled the question of what is an electropositive metal, we are now able to answer why weren't they isolated before 1800. The reason they were not isolated before 1800 was electricity itself was undiscovered at the time. In order to liberate and separate these electropositive materials from their natural found state in other compounds, you would need electricity to liberate them. As a result of the fact that electricity wasn't invented in the 1800s, it basically means that we were unable to separate them and actually find them on their own. The buzz term in this that you need to make sure that you include is the fact that electricity itself was undiscovered at the time. Another effective, or should I say, acceptable answer in this case would be saying that the electropositive materials and metals themselves were actually too reactive and as a result were unable to be isolated on their own. That would also get you your full marks. The total marks going for this question was only 3 because it was yet again another simple one-line answer, and you got 3 marks for making sure to say that electricity itself was undiscovered at the time, in this instance the 1800s. In part 6 here we are asked to refer to the electrochemical series to explain why only some metals are found free in nature. So one thing we have to do here is kind of understand what it means by finding them free in nature. Most metals tend to be found in the form of salts or even oxides, and as a result, very few metals are found kind of in their pure elemental form. If we take something like aluminium, for example, aluminium is actually very, very rarely found on Earth in its pure form, and it generally exists in the form of other forms of minerals, salts, and oxides. So the question here is, we need to use that electrochemical series to explain why this is the case, and actually very few metals are found freely. And the answer to this question goes as follows. In reality, only some metals are found freely in nature. Metals at the bottom of the electrochemical series, so bottom here being the important thing to notice here, at the bottom of the electrochemical series are less electropositive. And kind of what this basically means is that the less likely the metal is to have reacted with something else, for example, forming something like an oxide or a salt even, the more likely it is to be found freely in nature. You can approach this from several different ways. In this case, I approached it looking at the electrochemical series and how metals at the bottom are less electropositive. But another way you could say this is metals lower down the electrochemical series are more difficult to oxidize, or they're more easily reduced. And these both basically accomplish the same answer. Either way, it's just explaining how the less likely the metal is to have reacted with something else, the more likely it is to be found freely in nature. And the marks for this question were fairly simple. There was 3 marks going in total. The total number of marks going for this question was 3. In this case, the buzz terms that you needed to include were the metals at the bottom of the electrochemical series are less electropositive. And as I was saying earlier, you can approach this question from another standpoint, saying that metals further down are more likely to be reduced, or they're more easily reduced, should I say, and the opposite is also true, that they are more difficult to oxidize. Either way, that's how you get your 3 marks for this question.